So, hello everyone. I'm Subhajit Dandapat. So, I'm a theoretical research scholar at Tata Institute of Fundamental Research, Mumbai. So, today I'll be giving a brief overview of the famous Heisenberg uncertainty principle that you may have aware of. So, the theorem says the more accurately you want to measure the position, the less accurately you know the momentum. And vice versa. That is, the uncertainty in measuring the position is inversely proportional to uncertainty in measuring the momentum. That is, delta x and delta p equals to some constant. So, more precisely, that constant is at least the half of the reduced Planck constant. So, this is the uncertainty principle. So, in a more accurate way, this equation 1 defines the uncertainty principle of position and momentum. So, where the uncertainty of getting the position times the uncertainty getting momentum, which is at least equals to the half of the reduced Planck constant, where reduced Planck constant is given by h by 2 pi, where h is the Planck constant. Now, let us have a brief physical overview of the uncertainty principle. So, now let's say you have a rope and which is attached to the other end of the well, let's say here, and you are giving a rhythmic shake to that rope. Now, in this scenario, if I ask you where the wave is located, then this question seems unreasonable to you because the wave is spread to the entire length of the rope, so you don't know exactly where the wave is. But if I ask you what is the momentum of the wave created, so then you can possibly then you can possibly answer this question, because here you can, from this you can easily get the wavelength. Wavelength is basically the distance between the two peaks of the shake of the rhythmic waveform. So let's say the wavelength is lambda, and from the de Broglie formula you already know that the momentum is related to the wavelength via the following relation: p equals to h by lambda, where h is the Planck constant. So now you can easily measure the wavelength from this, and then you can easily measure the momentum via this formula. So in this case, we have the well-defined momentum but ill-defined position. Now let us look at the at a second scenario where you are giving a certain, so we have the same situation. The rope is attached to the other end of the wall, but in this case, instead of giving the rhythmic shake, you are giving a sudden jerk to that rope, and that's why a sudden bump is created at the center here. Now, if I ask you where is the wave located, then you can answer the wave is located most probably at the center. But if I ask you what is the wavelength, then the wavelength, and it is clear from the picture, the wavelength is actually destroyed. So there is no specific wavelength defined here. So that's why you can't define a momentum. So in this case, the momentum is ill-defined, but the position is well-defined. So this is basically, so that means you can't measure position and momentum simultaneously. So in the first case, you can measure the position in a proper. You can't measure the position, but you can measure the momentum in a proper way. But in the second case, you can measure the you can measure the position, but you can't measure the momentum in a proper way. So that is basically the physical interpretation of the Heisenberg uncertainty principle. So now let us look this the uncertainty principle from a generalized point of view. So more generally, for any canonically conjugate pairs, let's say we have two operators A and P, which obey certain commutation relation. That is, the commutator of AB is not equal to 0. In that case, that are basically known as canonically conjugate of pairs of operators. Now, in that case, the uncertainty in getting the uncertainty of measuring A times the uncertainty of measuring B is at least this term, where this denotes this Langeland wrangle that denotes the expected value of that quantity, and this is basically the commutator, means that is AB minus BA. This A and B, A can be position operator and B can be momentum operator, or they can be any other operator, like A can be energy and B can be time, and so on. So this is the most generalized principle. So we'll give a proof of that the generalized equation 3 in the upcoming slide. But for the time being, let us apply the formula for in our earlier case. That is, if A is X and B is P, then and what will happen? What will we get from this formula? In this case, this basically the commutator. In this case, basically we need the commutator of X and P. But from the basic quantum mechanics, we already know that the commutator of X and P equals to I h bar, where h bar is the reduced Planck constant. And if we put this into this equation 3, we'll easily get that delta X times delta P equals to h bar by 2. So in this way, we have verified our earlier formula. That is basically the position and momentum uncertainty principle, which is the which is generally known. Now let us prove this equation 3. For any operator, the uncertainty of getting uncertainty of measuring and that operator is given by that is basically the statistical standard deviation sigma A. So if we know that is sigma A square is basically expected value of A minus expectation of A square, this thing, right? So here the expectation means basically the quantum expectation. So that means that is psi A minus A expectation value of A times A minus expectation value of A psi. So if we denote this by F, let's say that is basically K of F, then this thing is basically bra of F. So that is sigma A square, basically bra of F inner product with K of F. So that's the thing. So here this is the sigma A square equals to inner product with F and F with itself. Now I'll take another operator, let's say B. If we apply the same principle, then basically, and if we define G like the following way, then is basically the uncertainty of getting B is basically inner product with G with itself. Now we need two relations and to prove the this formula. The first one is the Schwarz inequality, which is basically this one, and the second one is a general basically which comes from the basically general understanding from of a complex number. So the first thing it says that inner product with F with itself and inner product with G with itself is basically greater than equals to the inner product with F and G is mod square, which is the Schwarz inequality. This you may have from the basic from of complex analysis. And the second one is the most obvious thing, because that is if we take any complex number and take their mod square, then we will get basically real part of z plus imaginary part of z square, and basically sum of two square is basically greater than equals to the sum of the individual square. So from this we will get this, and basically imaginary part of any complex number, let's say z, and basically we already know basically it is z minus z star by 2i, which is basically this square. So we need these two formula for proving our uncertainty principle, generalized uncertainty principle. Now basically the sigma a square and sigma b square from these two equation 7 and 8, and which basically there is a inner product with a itself and g inner product with itself. So which is basically if we apply this square inequality there, will basically this. Now let's say our complex so inner product with any quantity is basically a complex number. Let's say fg equals to z. So if we take the conjugate of this complex number, there is basically it is gf, like, so this will be inverted if we take the conjugate. Now if we apply this principle, now let's say f and g equals to z and g and f equals to z bar, and f of g equals to it is also already z. So now if we apply this equation 10 here, we will basically get this one. Now what is our next goal? Now our next goal is to calculate these two, fg and gf. So it can be shown that fg equals to and gf equals to these two quantity. So let us okay, I will give you a big proof of that. So now let us give you a look into the proof. Now so just a minute. Okay, so f inner product with g is basically it is basically the wave function psi a minus average of a minus then, and what is this g? G is basically b minus that expectation of b psi, right? Now if we break this, then we'll get psi ab minus ba. These averages are just a numbers, so you can also pull it out in a bracket. Okay, whatever. So now which is basically this thing plus a b psi. If I further break this relation, we'll get psi ab psi. Since this is just a number, you can pull this thing outside the bracket. And similar for the next one, psi b psi, and for the third one also you can pull both of ab outside the bracket. So this is this thing. Now how the wave functions of the quantum mechanics are normalized, usually normalized. So this thing is basically equals to 1. Now what is this thing? This is basically expectation of AB. What is this thing? This thing is basically expectation of A. So now, so that is expectation of A, expectation of B. What is this thing? This is basically expectation of B minus expectation of A, expectation of B. This thing is basically expectation of A, expectation of B. So this and this cancel out. So we are left with AB minus AB. Similarly, if we take the inner product with G and A, we'll get BA minus AB. So this is the thing. Now, yeah. So these two formula we recently proved. Now our next goal is to subtract these two relations, 12A and 12B. So if we subtract this, then we basically get these two will be cancelled out. Then we will be only remaining with AB minus BA, then which is basically commutator of AB. So this is the thing. Now after putting this into equation 11, we were finally left with this famous generalized uncertainty formula, this thing. So we have proved this one. Now Now let us apply this to various operator and derive the other uncertainty relation other than the position and momentum uncertainty principle. Okay. So the first famous uncertainty principle is the energy and time uncertainty principle. It says the general meaning of the energy time uncertainty principle is that a quantum state that exists only for a short time cannot have a definite energy. The reason is that the frequency, let's say nu, of the state is inversely proportional to the time, because frequency, if you take the if the unit of the frequency basically hertz, which has the unit of second inverse. So that is the thing. So and the frequency connects with the energy of the state, right? So that's the thing. So that's why since the frequency is it is proportional to the energy, because E is kind of in the order of h nu. So that's the thing. So basically E is order of 1 by t. This is a rough estimate. So that's why the uncertainty of getting the energy and uncertainty of getting the time is constant, basically constant. Okay. So that means so if you want to measure the energy in good precision, the state must be observed for many cycles. So that's the thing. So that's the rough physical interpretation. So for this we need to prove the there is a typo, it is minus I h bar. So energy and time, if you let us evaluate this energy and time computation relation. Okay. Now energy is basically the Hamiltonian operator. The energy operator is basically the Hamiltonian operator, which is minus I h bar d by dt. So now if I want to evaluate some commutation relation, we need to act this relation on some state psi. Then we'll get, if we now break this energy operator into the time domain, now then if we apply this, the first thing we'll get, the first term will give you I h bar d by dt t psi. The second term will give you minus t minus I h bar d psi by dt, right? So now the first thing is dt by dt equals to 1, so we are only left with psi, and the second thing minus I h bar t d psi by dt if we break this derivative. Now this will give you the third term, this term will give you plus I h bar t d psi by dt. So these two terms cancel out and you are only remaining with I h bar psi. That is, energy and time is basically, the computation of both is basically I h bar. So this is the thing. So this is the formula. Now we apply the same relation inside the mod. So since we are applying inside the mod, so delta E and delta T is greater than equals to minus I h bar by 2I mod, and if we take the mod of negative sign, it will give a positive h bar by 2. So this is the famous energy and time uncertainty principle. So you can obtain the uncertainty principle for any two non-commutating operator. So let's for deriving the, let's say, energy position uncertainty principle, you can take the first operator to be your position and second operator to be your energy. That is basically energy. B is basically energy because this is the kinetic term, p square by 2m, and this is the potential term. So then if you compute the computation relation of A and B and then put it inside that generalized uncertainty principle, that is equation 14, then you will ultimately get the uncertainty of measuring x time uncertainty of measuring energy, which is at least h bar by 2m times expectation of p. So that you can easily get. So this is another uncertainty principle that you can convey. So basically, so there are you can also obtain various uncertainty principle, other uncertainty principle for any non-commutating operator. So this is what I wanted to say about uncertainty principle. So thanks for your attention. Thank you.